Good afternoon, everyone. Thanks a lot for watching my presentation. My name is Mingchao Yu. You can just call me Fisher. I am Chinese, so yeah, you can't see me unfortunately. Today, I would like to introduce you to a new hash accumulator called coded Merkle tree, which solves a big threat to scalable blockchain systems called data availability attacks. This is a work I did when I was a postdoc in USC, so I would like to first thank my colleagues, Saeed, Songze, and my supervisor, Professor Salman from USC, and my collaborators, Professor Sriram from University of Washington, Professor Pramod from UIUC, as well as our sponsor, Trifecta Blockchain. The presentation will be organized as follows. I will first provide a motivating example, which is blockchain light node. I will then formally define the data availability problem and introduce you to the basic idea behind our solution, which is called erasure coding. I will then describe our solution in detail and finally share with you its performance and implementations. In a classic blockchain system, every node maintains the entire blockchain, including both the blocks and their headers. But this is not scalable due to its expensive storage and communication costs. Thus, a scalable blockchain system should also admit a new type of nodes that only store the headers. Such nodes are called light nodes. A light node could be a client in a simplified payment verification system or a node from a different shard in a sharding blockchain system. But since a light node does not download any blocks, how can you decide to accept a block header or not? The classic solution is simply wait. A light node waits until the block to be deeply buried in the blockchain before accepting its header. In our example here, a light node waits for 4 epochs before accepting a block header. In general, longer waiting yields higher confidence. However, this method has an obvious disadvantage, a very high confirmation latency that could be hours. A more promising approach is to build a blockchain system where light nodes can rely on honest full nodes in the system to alert them about invalid blocks. This way, a light node can set a short timer based on the network latency, and if it does not hear any alarm against a block before the deadline, it will accept the block header. However, this solution also has a hole. An adversary block miner can attack light nodes by publishing the header of an invalid block but hide the block body, so that honest full nodes cannot audit the block body and alert the light nodes. This attack is called data availability attack. Due to this attack, before accepting a block header, a light node must first check by itself that the entire block has been published and is available for auditing. But data availability check is very difficult. This is because an adversary miner only needs to hide a very small portion of a block to hide a fraud transaction. Such a small hiding can hardly be detected by a light node unless the light node downloads the entire block. Now, I would like to formally describe the data availability problem. We assume there are 3 kinds of nodes in the system: malicious full node, honest full node, and light node. We assume every node is connected to at least one honest full node. We also assume that every honest node will rebroadcast whatever information they have received. By these assumptions, what we really try to say is that whatever information captured by one honest node in the system will eventually be known by all the honest nodes in the system. And also, we do not assume honest majority, which means our solution will work even under dishonest majority. Under such a system, if a block has been fully published, then the honest full nodes in the system will be able to verify this block and alert all the light nodes in the system if the block is fraud. Therefore, a malicious miner is motivated to hide the block body. So, the data availability problem is that when a miner full node or a neighbor full node recommend a block header H, how can a light node who only has the header to check whether the block body is fully available in the system or not? To this end, the only thing a light node can do is to sample the block body and rebroadcast. But how can you make sure that every bit has been published without downloading the entire block? The key to this problem is erasure coding. So, how could erasure coding help? First, what is erasure coding? Assume our block has 4 data symbols. By erasure coding, what we do is to generate parity symbols by linearly combining them under a finite field. In our example here, we generate 4 parity symbols using the very well-known Reed-Solomon code. Now, we have 8 symbols in total, and any 4 out of these 8 symbols, or more generally, any 50% of these symbols will allow us to fully recover all the symbols. Now we have a coded block. What we require the miner to do is to generate a Merkle tree based on this coded block and ask the miner to publish this Merkle root with the block body. The rest of the tree does not need to be published because other full nodes can recover the tree using the block body. How could this structure stop miners from hiding? Let's assume the block miner puts a fraud transaction in the first symbol M1, and let's see what will happen when light nodes challenge this miner. When Stuart asks for M2, the miner will happily disclose it, as well as its Merkle proof. Similarly, when Bob asks for M4 and Dave asks for P3, the miner will also happily disclose. But up to this point, the miner will not disclose any new symbol because this new symbol will enable decoding. Therefore, there will be only 3 symbols available in the system up to this point. So, when any light node challenges any foot node, you will have 5/8 chance to catch an unavailable symbol. So, by keep sampling, the probability that it will not catch a missing symbol will decrease exponentially, which means the number of samples needed per light node is basically a constant. To counter erasure coding, instead of hiding, what the malicious miner can do is to generate rubbish parity symbols, which won't allow the recovery of the block. It then publishes the entire tree except the first symbol M1. Since almost everything is published, light node can hardly detect the hiding of M1. The good news is that honest full node can detect this and prove it. Once a full node receives 4 symbols, you will recover the block and reproduce the Merkle root. If the reproduction is failed, it knows that the coding is incorrect. It can then send these 4 symbols to light nodes as an incorrect coding proof, so that light nodes can redo the verification and reject the block. But the proof size here is 4, which is the block size. This is prohibited because our goal is to save the light nodes from downloading the entire block in the first place. Before we move on, let's summarize the costs of the solution we just described. This solution is called one-dimensional Reed-Solomon, or 1DRS, because it uses Reed-Solomon code to generate one coded block. With this solution, a light node only needs to download one Merkle root and only needs to sample a constant number of symbols and their Merkle proofs. Both are optimal. But 1DRS requires a prohibitively large incorrect coding proof size of k. Moreover, the encoding and decoding complexity of Reed-Solomon code is k squared, which will make it unusable for large blocks. To reduce the incorrect coding proof size, the solution proposed by Mustafa, Alberto, and Vitalik is to divide and conquer through two-dimensional Reed-Solomon code. More specifically, the k-data symbols of block are placed as a square. Then 1D Reed-Solomon code is applied to every row and every column. This way, the protection is reduced to a set of much smaller 1D Reed-Solomon protections, each with its own Merkle root. As a result, 2D Reed-Solomon has a root download cost of 4 square root of k, a sampling cost of a constant which is greater than 1DRS, an incorrect coding proof size of square root of k, and a complexity of k to the power of 1.5. Our goal, then, is to push every cost down to its optimal. Finally, we are ready to introduce our solution. To derive our solution, we first ask ourselves, what should an ideal solution provide? Well, an ideal solution should admit a root download cost of 1, which means the coding must be one-dimensional. It should also admit a constant sampling cost, which requires a good code. An ideal solution should also admit a constant size incorrect coding proof and a complexity linear to the block size. To achieve these two, a low-density erasure code is needed, which means each parity symbol is a linear combination of a very small and constant number of data symbols. For example, P1 is equal to only M1 plus M3. Moreover, when a full node decodes, it should only solve one equation at a time, so that it can narrow down the incorrect coding to one equation. Putting all these together, what we're looking for is a class of good low-density parity check code, aka LDPC. The reason why I say class is that we will need different codes for different blocks of different sizes. We searched the literature and did find such a class. It has an equation size of only 6, and when iterative decoding is used, any 87.6 of the coded symbols can recover the block. Now you may think, okay, the job is done. Nope, it is not. A big challenge is waiting for us. The challenge is caused by a new attack where the miner does the coding incorrectly and then hides the hashes. Assume we apply a low-density code where P1 equal to M1 plus M3. The malicious miner generates rubbish parity symbols and publishes everything except M1 and its hash H1, so that the hiding is small enough to dodge light node sampling. Then, when a full node receives M3 and P1, it will try to recover M1 by P1 minus M3 and verify M1 against its hash H1. But there is no H1, so the full node cannot verify M1 and the decoding will stuck there. Since every equation can go wrong, what this means is that our idea will only work if the entire layer 1 hashes are available. In other words, light nodes will also need to check the availability of layer 1. Okay, let's recap what is going on. What we have done is to partition the block into data symbols, generate parity symbols using them, and then compute the hashes of all the symbols. The new problem is to ensure the availability of these hashes. So, we batch these hashes into data symbols for layer 1, and then apply a shorter low-density erasure code to it. By doing this hashing and the erasure coding iteratively, the problem becomes smaller and smaller. And eventually, we will obtain the Merkle root, which does not have availability problem because it must be published. And this is coded Merkle tree. You may have noticed that we interleave the hashes of data symbols and parity symbols. The purpose is to enable efficient light node sampling. When a light node requests a base layer symbol, its Merkle proof will automatically sample one data symbol of every higher layer. Moreover, since every higher layer symbol contains the hashes of both the data and parity symbols of its child layer, the light node can further sample some extra parity symbols from each layer at zero Merkle proof cost. With this efficient sampling, there is no way for a malicious miner to hide. Incorrect coding attack will not work either. This is because an honest full node can recover the coded Merkle tree layer by layer from the top. The hashes carried by a recovered layer will be used to verify the recovery of the next layer. When a broken equation is discovered during the recovery, the honest full node will share this equation and the associated hashes to the light nodes as the incorrect coding proof, so that light nodes can reject the block. So, we have completely shut down the malicious miners and cracked the data availability problem. Here is its performance. Coded Merkle tree only requires one root to be downloaded. It only requires a constant number of samples per light node. It also offers an incorrect coding proof size of only 6 symbols and enjoys a linear complexity. Its only drawback is that the sampling cost is higher than 2D Solomon due to that low-density coding is more vulnerable to missing symbols. But since the cost is a constant, it is negligible with increasing block size. Implementation side, we have already developed a coded Merkle tree library for both Python and Rust. And coded Merkle tree has been chosen by Trifecta blockchain as its data availability solution. In summary, coded Merkle tree optimally protects light nodes in blockchain systems from data availability attacks at almost constant costs. We say almost only because the Merkle proof size will increase at a log speed with the block size. Coded Merkle tree is very simple to implement. We just need to add the coded Merkle tree root to the block header or to a special smart contract to enable the protection. Moreover, while coded Merkle tree is developed to scale blockchain systems, it can also be used for any decentralized systems that are vulnerable to data availability attack. Have you ever been bothered by data hiding? If yes, please consider coded Merkle tree. Thank you.